right, we are back. We're still doing recursion in Haskell. Getting better at it, I suppose. And now we're gonna sort lists, I guess. Right, we have a list of items that can be sorted. Okay, sure, we can have that. Their type is an instance of the ord type class. That is what it means. If they can be sorted, they're part of the ord type class. If I remember correctly, yeah. And now we want to sort them. There's a very cool algorithm for sorting called Quicksort. It is a very clever way of sorting items. While it takes upwards of 10 lines to implement Quicksort in imperative languages, the implementation is much shorter and elegant in Haskell. Quicksort has become a sort of poster child for Haskell. Oh, okay. I don't know the clever algorithm for sorting, unfortunately. Therefore, let's implement it here, even though implementing Quicksort in Haskell is considered really cheesy because everyone does it to showcase how elegant Haskell is. Alright? So we'll be cheesy. Soon you will know, says Colgating on tap. Oh yeah, soon we will know the algorithm for Quicksort. Alright, so the type signature is going to be Quicksort. We take, an ordered, has to be the ord type class, and we take a list, and we get a list. No surprises there. Yep, no. The edge condition, empty list as expected. That was expected, yeah. A sorted empty list is a sorted empty list is an empty list. That's the edge condition. Now, here comes the main algorithm. A sorted list is a list that has all the values smaller than or equal to the head of the list in front, and those values are sorted. Then comes the head of the list in the middle, and then comes all the values that are bigger than the head. They're also sorted. Alright, let's go through this one more time. Right, a sorted list is a list that has all the values smaller than or equal to the head of the list in front. And those values are sorted. Alright, I think one thing we could do here is we take just this one. Quicksort. Actually, the music is a little bit too loud. Is that better? That's probably better. Right, Quicksort. We take one of these. No surprises, indeed. And then we take a list and we get another list. All right. All right. So, Quicksort. If we get an empty list, then we return an empty list. All right. I'm assuming it's just gonna be one line here. All right. Quicksort. Right, we took the head, right? XS. Right, a sorted list that has all the values smaller than or equal to the head. In front. And those values are sorted. Okay. So, this feels like it's a double recursion kind of thing. Right, because we put the head in the middle. No, we need a guard, not pattern matching, since we're doing... right, we need a guard. Right, if the head of XS... Right, that's what we do. We compare the head... No. We need a value. That's the head. Aaron Cyrus, is all this you're learning available for free? Yep. It's here, right here. learnyouahaskell.com. I think, as far as I'm aware, this book is like probably the de facto one. If you want to learn Haskell, this is the recommended book. And it's, yeah, it's completely free and available online as long as you have access to the internet. Or, well, you don't have to have access to the internet. I guess you could just go and print it out in your local library and learn it from there. Yeah. Learn You a Haskell Real Good. That's the name of the book. Right. Let's think here. If X is smaller... Oh shit, I forget the syntax of these things. Then the... Do I need the 3 values for this? No, we're gonna do it recursively, right? So, we're gonna is... Quicksort. Damn it. List comprehensions. Oh, right. Let's do list comprehension. Nice. Aaron Sears' syntax is a sin. Is sin. What do you mean? Alright, we do a list comprehension. Alright. Thanks for the tip, because I was just gonna feel that, nope, I'm getting out of here. Is it enough with 1 list comprehension? Right, we do have a cheat sheet. Let's see, we can search for list comprehensions. Right, we can use the cheat sheet for syntax, right? Let's try that just in its lonesome. We take X. No, wait. Alright, let's do X is the list, right? That's... Right, we take the list and we do it for... Here we are. That's the entire list. In this we would just get the normal list, right? But we do we... I don't know. Aaron Sears means I struggle with it. Oh, right, yeah. The syntax of Haskell. Oh, man, it's... Just wrapping my mind around Haskell is... It's difficult. It's difficult. Right. We need some sort of way to make sure the placement, right? That is what we're trying to do here. Trying to get the placement, right? Where if X so I guess the recursion will happen in here. Right? If maybe not. What about if we add one of these? We only add it if X is smaller? Greater. Shit, I forget. Is this the first item of the list or the last item of the list? Let's try it this way, alright. Bigger than, well, either way it would get sorted, right? We take X is bigger than no, smaller than the head of the other list, right? Quicksort. No. Right. Here we go again, using multiple different values. Colgate says, don't use the same for head parameter and list. Yeah, right. I was just thinking about that. Yeah, that's weird. Let's use I, because that's what we do in Python. There we go. We go through the list, but we put a, what do we call those? This is press something. So we only take X. This won't work. We don't get everything from here. I think it's time to test this though. What happens when we do this? I need to test it out. Alright, so we go over here. See if it even will be reloaded. Nope. Alright. This will be weird, because what do we get? We get a list. I mean, the syntax of the list comprehension is good. It's just this that is the problem, yeah. Oh, is it if... No, if I is smaller than X. What happens now? I mean, this won't work, but let's see what happens. Right, and then we do Quicksort. We give it a list with 2, 42, 1, 38, and 5. Sure. Yeah, exactly. We only get... We're on the right track. We just need to do this recursively until the list is empty. So how do we make the recursive call? Where do we make the recursive call? I mean, one way of thinking outside of the box is just... No, that's not a good idea. Alright, I need to check the syntax of list comprehensions again. Alright, a list comprehension consists of 4 types of elements: generators, guards, local bindings, and targets. This is different than what they did. Tab says you also miss the head and bigger elements. Yeah, we'll get to it. A list comprehension creates a list of target values based on the generators and guards given. This comprehension generates all square. Wait, this is just confusing lingo. This is not how we learned it. So, also I'm a bit worried that since everybody show off Quicksort, I'm afraid that one of these things is gonna be Quicksort. So I kind of... Do you know? Is one of these things Quicksort, Colgate-In-On-Tap? It was you who gave me this cheat sheet, so you can know if I should stay away, because I don't want to get spoiled quite yet. Yeah. They are not. Nice. So I don't have to worry for checking that out. But let's go with your tip first. Alright. We missed the head and bigger elements. Alright, one spoiler I can ask for. Is it all within one list comprehension, or do I use multiple list comprehensions and like put them together, right? Do I do this? No. It's probably just, since it's elegant, it should be only one list comprehension, shouldn't it? Oh, I'd use 2 and ++? Alright. You would do it this way. Alright, so what if we just do the same thing? It's still not recursive, but... Alright, just to try and see... Oh, that doesn't work. Oh, I was gonna do that. Curious, like what just happened? Right, there we go. 142. Well, it doesn't work. 5 ends up in. Actually, can we? What is happening here? All right, this one takes one over here. I don't quite know what's happening. Remember ++x to the middle of the comprehensions. Oh. But that's 3. All right, so you mean like this? Wait. In the middle of the comprehensions? To not miss out on the head. Right, we're still doing something wrong because the 5 ends up in the completely wrong place. Why does it end up in the wrong spot? And we're not using recursion either, are we? Oh, do we just... No. Something is problematic, yeah. Aaron Sarah says, you only learn about input and output in the 9th chapter of this. Seems like such a basic and important thing to me. Yeah, we've been joking about that, yeah, Aaron, that we just learn about Hello World. Oh, we'll learn about Hello World in chapter 9. We're not allowed to, we're not supposed to do programming before chapter 9. It's kind of messed, yeah. Oh, right. We're gonna check the astral projector thing. Just a short break from Haskell to see what this is. Astral projector, lightning resistance, we get intelligence, spell damage, avoid elemental ailments, nice. Nova spells has less area of effect. Nova spells deals 30% less damage to players. Nova spells, oh, targeted location instead of around you. There we go. That's how you do it. That's interesting. Looks like fun. Less damage to players. There is a Nova, right, where you explode and deal damage to yourself. In Chaos Damage Nova, something like that. I don't remember. You just need to add recursions. I was kind of thinking, do I just do this on the entire list? But that won't work. Oh, I do it on the... But on Wolfmonkeys, the strong boxes have a lot of Nova effects. I think Atzeri has them beyond the bosses. Oh, right. Of course, I was just thinking about self-damage, and that doesn't happen very often. Never mind, not Atzeri. Okay. Right. So what do we do here? Actually... If we take like a... Right, the first one, it takes the smallest number and put it here. Wait, no, X. It takes our head, which is 2. Ah, that's what we're doing. That's what this whole thing is doing, right? It takes, from this list, it takes number 1 and puts it to the left. It takes the head, which is 2, and puts it in the middle. And it takes 42 and puts it to the right. Where does these two things come from? 138 and 5. Because this one only takes... This one should only take 1, right? Oh no, if it's smaller than X and if it's bigger than X. No. So it takes all of them. Right. So wait, do we just do this? Is it this easy that we just quicksort this entire list? No, that won't work. That won't work. Right, I think this will even break it, won't it? Yeah, That's what I thought. It just does it over and over and over again. Yeah, it compares elements to the head. Right, so that's what we need to do. We need to change which head. We should stop using that head. We should use another head. Yeah, so we should call it on... The recursion should happen over here, right? Because the first one is fine, and then the second one is fine. It's just... Right, we don't have to call... This is it, right? Quicksort. This one. Let's try it out. And there we have it. Right, because, yeah, we place... That's what we do, right? We took 3 numbers. That is what we were supposed to do, right? We take the head, we put it in the middle between 2 things. We could do it the reverse way around as well, if we wanted to. Right, close. Are we not done? Did I miss something else? Add a quality to one of them so you don't miss the... Oh, the equal. Right. Yeah. Smaller than or equal. Easy miss to make. Oh yeah, and it doesn't matter where we add them. Does it? Oh, wait. No, I think we have to add the quality check over here. Don't we? Shit, which order is that? Equal like this. I think that's the order. Yeah. And remember to sort the smaller list as well. Wait, do I have to sort this list? What do you mean the smaller list? Isn't this guaranteed? Right? We always take the absolute smallest number here. That's what we're doing, and over here we take the rest of the numbers. And it doesn't matter? Okay. Try 3, 2, 1. Alright. 3, 2, 1. Right, so it takes... Why does this happen? Right, the head is... Oh! Because the head is 3. It's gonna take, since 2 is smaller than or equal, it's gonna put 2 in the front, yeah. So we do have to... wait, is this enough? Quicksort? Oh shit. Yeah, we do have to do the double recursion, yeah. Thanks, I like that. Try 3, 2, 1. Yeah, because it does... It just takes the first one, right? Yeah, it's lazy. It didn't take the smallest one. It just took the first smaller one. That was my mistake. Yeah, I was thinking that this thing took the smallest, but it doesn't. It just happened to on my list. Because the head was 2, it happened to be the only one smaller was 1. So it was just randomly worked out because of my list. Alright, there we go. Aaron says, so this is why you say imperative programmers are liars. You also can't set a variable to something and then set it to something else later. Yep, it is. If you say that A is 5, you can't say it's something else later because you just said it was 5. What are you, some kind of liar? Exactly, yep. That was the first page of the Haskell book, yeah. He called us liars, so therefore we call ourselves liars. Alright, so double recursion. We got there, finally. Right, so the algorithm, let's read it again now that we have done it. Right, a sorted list is a list that has all the values smaller than or equal to. I forgot about that. Then the head of the list in front, and those values are sorted. Exactly. All the values. I just put one value. Then comes the head of the list in the middle, and then comes all the values that are bigger than the head. They're also sorted. Yeah, exactly. Double sorting. That's what he alluded at, yeah. 2 times in this definition, so we'll probably have to make the recursive call twice. Indeed. Also notice that we defined it using the verb is to define the algorithm instead of saying do this, do that, and then do that. Yep, that is what we did. I think it's starting to sink in. The functional that we define things, what they are, not what they do. Oh man. We've been reading this for 1.5 weeks soon. And it's starting to sink in the idea that we're always saying what things are, what it is, not what it does. Right. That's the beauty of functional programming. How are we going to filter the list so that we only get the elements smaller than the head of our list and only elements that are bigger? List comprehensions. I think it would have taken me a long time to get to list comprehensions. Yeah. So let's dive in and define the function. Wait, what is this? They did it way differently, eh? Colgitino says grasping it several chapters before Hello World is pretty cool. Oh, it's starting to sink in. I'm not grasping it yet. It's like I see the light in the end of the tunnel. I can see land on the horizon. It's more like that. Yeah. Alright. They make a smaller sorted. Oh. Right. Actually, I like this better. Do I? Yeah. Mine is kind of, if you just look at it, it's kind of a mess. This here is, you take the smaller sorted, and you have X, and you have the bigger sorted. Yeah. I mean, calling it elegant, right? This is not elegant. So yeah, I like this way of doing it. Yeah, I like that. If we're actually doing 2 recursions, if we're taking a smaller list and we're making a bigger list, this becomes easier to read. Yeah. But this is the same, yeah. It has to be the same because that's how a functional language works. This is how it's defined. Let's give it a smaller test to run to see if it appears to behave correctly. Nice. You could use where. Right, you would just flip it around then, right? Smaller sorted, we would write this and then add where and do these two things after, right? Just flip them around. That would be even prettier, yeah, because that would actually... Let me show you why I would think that's prettier. Alright. Right. Well, we don't need let here. What we do is we put this here. Right. Syntax is not going to be great, but whoops. No. Right, smaller sorted, and then... Oh shit, I don't remember. Did where here? I don't remember syntax, but right, yeah. No, it's... something like this. Which, I think that's just a personal preference thing. But I like this, that where we just... step down. We don't move back and forth, right? Instead we just indent once and then we indent again. I don't remember if where ends up here or here. It doesn't matter, right? But what happens is that we indent and then we indent. And when we're finished with this syntax, we go back. Right? We go back to this indentation, right? So when we keep on building, we get further and further in, right? This is the syntax that happens when you use where. Instead of... I mean, I guess this here doesn't... Right? In the end, we start... I just assume that this could lead us to... I don't know. Maybe. Colgate in on tab says, I'd put smaller sorted ++ line, one on the function name line. Oh, right. Wait, do we need this line when we do where syntax? Right, if we have this thing, we have to indent, no? That is a mess, if this line is necessary. And it is necessary, isn't it? Yeah, it is necessary. So I would definitely indent after this equal sign. Oh, the same. Oh. Oh, yes. Yes. And then we put where. Ooh, I like this. Yeah. Like so. Yes. This. Thanks, colleague. This is beautiful. Now it is elegant. Does it work? Did I screw something up messing with the... Yep. What did I mess up? How did I mess that up? How is the error here now? Right, if an empty list. We didn't change anything, did we? We just changed how it looked. 2 quicksorts. Isn't it supposed to be that way? It was like that before as well. Why would the 2 quicksorts be breaking it? Wait, quicksort is defined twice? Oh! We have it up here, yeah. Oh, that's not... That's how you do a line comment in Python. And I'm assuming... Oh, shit. And that's a tab, wasn't it? There we go. Oh, man. I was like, just looking at this part and just like, what's wrong? Nothing's wrong. All right. There we go. Nice. Much prettier. All right. So that's the algorithm for sorting. For example, wait, put smaller sorted on the same line as where an indent bigger sorted as much as smaller sorted. Wait, do you want to change it some more? Oh yeah, you mean like in here? Wait, no. Wait, put smaller sorted on the same line as where? Oh, you mean like this? Like this? Oh, I can see why people would do it this way. It is pretty, yeah. Maybe to make me happy. No. No, you're right. That's probably the way to do it. Oops. Sneaked in a tab there somewhere. I need to fix my Vim so it stops doing that. Whoops. Ah. The where alone seemed quite lonely indeed, right? Right, it's like, where what? I mean, this would work, but... Actually, the benefit of this is that you get this gap, you get this empty line here to even show even clearer that, oh, here we're doing some where stuff. Alright, but now we're just messing with how pretty the text is. Alright. Alright, quicksort. Worked fine. Booyah! That's what I'm talking about. So if we have, say, 519467 and we want to sort it, this algorithm will first take the head, which is 5, then put it in the middle of the 2 lists that are smaller and bigger than it. Yeah, exactly. It will take... Yeah, it will take 5 and 9, so it will be 159. Wait, no. Yeah, 159. Take the head and then put the 2 lists that are smaller and bigger than it. So at one point you'll have 143 plus plus 5 plus plus 9, 6, 7. Yeah. We know that once the list is sorted completely, the number 5 will stay in the 4th place, since there are 3 numbers lower and 3 numbers higher than it. So if we sort 143 and 967, we have a sorted list. We sort the two lists using the same function. Eventually, we'll break it up so much that we reach an empty list, and an empty list is already sorted in a way by virtue of being empty. Here's an illustration. Nice. Here's the illustration. Oh, it actually, I was mistaken. I was thinking that it did, but it does both of them at the same time. Oh no, we have 5. Right. Oh, it puts all of them. That's something I missed. We take 5 and then we take... Yeah, of course. We get all of them. Right. 1 is smaller than 5. 9 is not smaller than 5. So we skip that one. That's our smaller list, right? Our smaller list goes through and says 1 is bigger. Okay, so we add it to this list. 9 is not, so we throw that away. 4 is smaller, so we put that down there. 6 is bigger, so we throw it away. 7 is bigger, throw it away. 3 is smaller, so we put it in. That's why we get 1, 4, 3, exactly. I like the coloring here, yeah. Same with 9, 6, 7, because that's the order that they are in. And we keep 5 in here. And 5 is going to just stay here. 5 is the sorted one. That's how it works. 5 is sorted, not the other ones. 5 has its place. Just like in here, 1 is going to get its place. And then 4 is going to get its place. And then 3 gets its place. Right? Yeah, exactly. Because it becomes an empty list here. Exactly. Nice. Tricky algorithm. Colleague Dinotep says, you got it. Well, I kind of got it. I won't remember it, but the next time I see this algorithm, I'll get it quicker. Yeah. An element is in place and won't move anymore is represented in orange. Oh, right. That's the orange. Boom, 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 boom. Boom, boom, boom. Exactly. Because it's the first item in the list that we sort. 5 gets orange, 1 gets orange, 4 gets orange. Yeah. If you read them from left to right, you'll see the sorted list. Although we choose to compare all the elements in the heads, we could have used any element to compare it against. In Quicksort, an element that you compare against is called a pivot. They're in green here. We choose the head because it's easy to get by pattern matching. Oh, right. I got it. Yeah. We choose the head because it makes sense. We could do it any other way, right? We could just take, oh, we're gonna take the third element in each list, but that's... Yeah. The elements that are smaller than the pivot are light green, and the elements larger than the pivot are dark green. The yellowish gradient represents an applicant's application of Quicksort. Exactly. Alright, we're back to trying to think recursively again. Aaron Sir says, should I install the Haskell language server? Alright, we've got... where was that again? I can show how I did it. Let's go to the table of contents. What you need to dive in. Where is it? The Haskell platform. What operating system are you on, Aaron Zero? I don't remember. I'm on Arch Linux, so I definitely went with the generic and got this one. Yeah, this one was great. GHC up. Just doing this one, that's what I did. And that works great. Otherwise, I would just, yeah, I would, if you have another, oh, you have Windows. Wait, here we go, Windows. The recommended way to install the components of Windows platform is using Chocolatey to install GHC and cobble install and follow the instructions at... I would assume that just following these instructions would be the easiest way to do it, yeah. I don't know, I haven't used Windows in a long time. I'm happy for it. Happier for it, yeah. Yeah, I used that, but should I install the language server? I think I did. I still haven't used it. I mean, if you don't install it, right, you won't need it for a while, I don't think. But if you start needing it, you could just install it later, right? I think I installed it just, I just pressed yes, 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 yes on everything. Because they said batteries included. If I don't... It's like Node Runner used to say. Do you have hardware space? How much hardware space does it take? Like none of it? If I ever run out of hardware space, it won't be because I installed the Haskell language server, I don't think. That was my logic. It's better to have it than not. If I ever will end up in that situation, that is. If I won't, I mean, if I uninstall Haskell, it's just gone, all of it, so. All right, thinking recursively. Wait. We did quite a bit of recursion so far, and as you've probably noticed, there's a pattern here. Yeah. Usually you define an edge case and then you define a function that does something between some element and the function applied to the rest. Yeah, usually go with the head. It doesn't matter if it's a list, a tree, or any other data structure. A sum is the first element of a list plus the sum of the rest of the list. A product of a list is the first element of the list times the product of the rest of the list. A length of a list is 1 plus the length of the tail of the list, etc., etc. Etc.? That's weird. I don't even know what the language server is. PowerShell just came with an error. Oh, that sounds awful. What's the error? Haskell people not caring about Windows users? Is it because Windows is not free and open source? I don't think so. I don't think so. Let's see. Of course, these also have edge cases. Wait. Right? Usually the edge case is some scenario where recursive application doesn't make sense. Right. When dealing with lists, the edge case is most often the empty list. When you're dealing with trees, the edge case is usually a node that doesn't have any children. I've never programmed with trees, actually. Never done that. It is similar when you're dealing with numbers recursively. Usually it has to do with some number and a function applied to that number modified. We did the factorial function earlier, and It is the product of a number and a factorial of that number minus 1. Such a recursive application doesn't make sense with 0 because factorials are defined only for positive integers. Often the edge case value turns out to be an identity. The identity for multiplication is 1 because if you multiply something by 1, you get something back. Right. Now we're looking at mathematics again. Yeah. I'm assuming that identity... Yeah. Also, when doing sums of lists, we define the sum of an empty list as 0. And 0 is the identity for addition. Yeah, where it... 1 plus 0 is 1. 42 plus 0 is 42. It's like 1 multiplied by 42 is 42. In Quicksort, the edge case is the empty list and identity is also the empty list, because if you add an empty list to a list, you just get the original list back. So that's our edge case, when it doesn't do anything anymore. I was oh damn it. Where it is nothing anymore. I was thinking that the edge case is where you try to stop it from doing something, but that's not how a functional language works. You don't do things, you define things. Yeah, I was thinking that, right? You try to stop it from going below 0. But that's not what we're doing. We're defining it, what it is. Not what it does. Oh man. So when trying to think of a recursive way to solve a problem, try to think of when a recursive solution doesn't apply and see if you can use that as an edge case. Think about identities and about whether you'll break apart the parameters of the function. For instance, lists are usually broken into a head and a tail via pattern matching, and on which part you'll use the recursive call. Aaron Sarah says GHC website says I must run PowerShell as a non-admin user. How do I do that? A non-admin user? I'm sorry, I wish I could help you with this, but I haven't run Windows in years, like I said. And when I did run Windows, I did not do it as a computer nerd. I didn't know any programming. I didn't... right? I never even sat in the PowerShell in Windows. And in Linux, that's just how you run things. You have to take an extra step to run as root, we call it in Linux, instead of admin. We're just inherently not an admin. So hopefully a quick internet search. Just search for how to run as non-admin Windows PowerShell. That'll probably get you there. This confused me a little bit. Try to think of when a recursive solution doesn't apply. And if you can use that as an edge case. Right, if I add two lists together, can I add an empty list? No, that doesn't. Well, it's weird. What do you mean doesn't apply? Think about identities and think about whether you'll break apart the parameters of the function. Yeah, if we break them apart, that's... If we have something and we want to break it apart into two things, or multiple things, if we need to do that, do again. Colgatino tab says, like with Quicksort, you can't compare to the head of an empty list. Right, yeah. I think this threw me off a little bit because the equivalent would be that because you cannot multiply by 1. But you can apply it, it just doesn't make sense, so you have to... So it's not quite the same, but yeah. Can't compare the head to a list to an empty list because the empty list doesn't have a head. There's nothing there to compare to. But that's where we start out when we try to figure out Haskell. We start out with this. Luckily in lists, we know now. And if we want to do something recursively for every item in a list, or not even every item in a list, if we want to do something for multiple items in a list, we do that recursively. And we know that the edge case will most likely be an empty list. All right. This is gonna take a while for it to sink in, but right? We're slowly getting there, I think. Slowly getting there. We're done with the recursion thing. Alright, definitely increased my knowledge of recursion. Hope you have as well. I think it's lunchtime, yeah. Lunchtime, actually. Just a quick spoiler. What's coming up? Higher order functions. Haskell functions can take functions as parameters and returns functions as values. Meta functions. A function that does either of those things is called a higher order function. So we can take a function and create a function. Higher order. It's like higher order of abstraction. Higher order of complication. Right, that is what's coming up.